Welcome back to Ontology Talk, and welcome back to this series on sets, logic, and inference. Today we've had an opportunity so far to talk a bit about sets and set membership and sets and subsets. Let's now talk about numbers. So it's interesting that in mathematics there had been a great deal of work up until the early 1900s, but there was a sense of crisis at that point. Why did we know that mathematics was true? How could we prove that mathematics was true? What were the foundations, and how did we know that the foundations were in fact legitimate for mathematics? And so Bertrand Russell and Alfred North Whitehead set out to do a really monumental task of creating these foundations, defining them axiomatically, defining them in logic, and proving that mathematics was true. Now, they weren't, in some sense, entirely successful, thanks to another mathematician, Kurt Gödel, that said ultimately that this enterprise was impossible. There was no both consistent and complete mathematics. But still, this effort did set straight the foundations of mathematics in many ways and remains a very important work in mathematics, and a fascinating exercise also showing how constructs of mathematics can be proven in mathematical logic. So set theory is the basis for mathematics. This is what Russell and Whitehead showed us. And they started with this extraordinarily simple approach, or it seems extraordinarily simple, that is just based on sets, and that sets can contain other sets. So we start with the empty set, the set that contains no elements, and the most simple set that is more complex than the empty set is the set consisting of the empty set. And we can continue constructing sets that are slightly more complex, sort of wrapping the previous set in another set construct. So there's the set of the empty set, the set that contains the empty set, the set that contains the set that contains the empty set, and so on. And so we arrive at a notion of a successor function, that a successor to a set is that set, a set consisting of that particular set. Okay. Each of these sets is different. Each of the sets contains only one element, except for the first set, which contains no elements. It is the empty set. And we can continue this exercise arbitrarily out to infinity. And another way to look at this is that each of these sets represents a number. So the empty set represents 0. The set containing the empty set is the representation of the number 1, and so on. So now we've turned the integers into set theory. So now that we've defined the integers with respect to sets and come up with this notion of a successor function, now we can start to do some interesting operations. And note the pattern that we have here. If we want to talk about 1, we talk about the successor of the predecessor of 1. The successor of 0 is 1. And this works for all of our numbers until we get down to a number that we can calculate immediately. Right? Our base case is that we know that the number 0 is just equal to the empty set, the first set that we've constructed. And so if we want to define addition, and that's denoted here by this a function, we have a base case where adding anything to 0 is that original thing. So the addition of x and 0 is x. Then we can also talk about the recursive case. And when we talk about the recursive case, we're essentially saying, well, I may not know how to calculate addition for the parameters you've given me, but I know that the answer is going to be the first argument plus the successor of something. Right? And if we know that that something is 0, then we're back to the base case. And so we can sort of recursively call this function continually taking the successor of something, and then that something is going to essentially be the predecessor of the argument. We're sort of walking back down this tree, or this recursive tree, to find something we know how to calculate. And then we can say that the answer is going to be the addition of these two things, and eventually we're going to get down to adding just this first argument to 0. We're essentially decrementing this second argument until we get down to an answer, and then we'll pop back up this recursive tree. So here's a sample calculation, right? So if we want to take the addition of the successor of 0, which is 1, and the successor of the successor of 0, which is 2, that's the same as adding the successor of 0 and the successor of 0, and then taking its successor, right? We've just done a substitution with this second sub-bullet from above. Right? And the calculation can then be answered, right? So we have the successor of 0 is just 1, which is the base case that we have here, the addition of 0 to whatever our first argument is. And then we can sort of back out the recursion to get our answer, and hopefully you can see how this works. And I would encourage writing a little Python program to actually implement this. And that So hopefully you've tried this in Python. Here's what it should look like. We're going to assume this same language where we have only the number 0 and these two functions, successor and addition. And we'll call this successor.py. Now, we don't have a way to do function substitution the same declarative way in Python, but here's a way we can come close. So we have our two functions, and if you give them a try, you can see that it will get the correct answer. So try playing with this and maybe even do a stack trace to see how the answer is derived. And you'll see that it's this same recursive process that we explored a moment ago. And if you want to go a little farther on this, try implementing multiplication. This will be a great exercise. And again, assume that we're using just the natural numbers, the positive integers plus 0. So we can do arithmetic with this numerical construction even without having an understanding of numbers. We just have sets, and our calculations are completely mechanical. It's an inductive process. We create a base case and a pattern, and then we execute this pattern recursively, simplifying and simplifying each time until we get down to the base case. So the definitions of addition and multiplication, if you gave it a try, are recursive. This is an incredibly powerful thing in computer science, and it's worth taking the time to work with these constructs and get familiar with them, because you'll find a tremendous amount of applicability of this general idea throughout your programming career, if indeed that's the path you're on. So recursion is one of the most powerful constructs we have in computer science. All right, that's a short lesson for today, and next time we'll go on to some set operations.